Hello all, my name is Aswathnarayan Radhakrishnan. I'm a PhD student at the Computer Science and Engineering Department at The Ohio State University. Today I'll be presenting our paper on enhancing the popular self-training framework called the Noisy Student. This work was done as part of my PhD research, along with my collaborators at The Ohio State University and the US Air Force Research Lab, as listed on the slide below. The main motivation behind our work stems from the training data-hungry nature of fully supervised deep learning methods. This becomes a huge challenge in domains such as remote sensing and medical imagery, where it's difficult to curate large benchmark datasets in the scale of ImageNet because the cost of annotation can be really high. In such scenarios, semi-supervised learning comes into play, as it can jointly leverage small sets of labeled data along with large unlabeled datasets for training purposes. In our work, we focus on one such technique called self-training by studying various design choices to enhance the learning capabilities of these models. Self-training falls under a popular category of semi-supervised learning techniques called pseudo-labeling. These models are generally trained in a teacher-student fashion, where an initial teacher model is trained on the small labeled subset and is then used to generate pseudo-labels on a large unlabeled dataset. We then train a student model on the combined set of both labeled and pseudo-labeled examples. We then use this trained student model as the teacher model for the subsequent iterations of self-training, where the same process is repeated multiple times to improve the quality of pseudo-labels. However, this training setup faces a problem called confirmation bias, which is the result of accumulation of noisy pseudo-labels which are generated as a result of incorrect pseudo-label predictions given by the teacher model. This results in the student model developing a bias towards confidently predicting incorrect pseudo-labels for the subsequent iterations of self-training, which can degrade the performance of such self-training models. In this work, we primarily focus on the noisy student self-training approach from Google Research. We try to tackle the problem of confirmation bias by looking at the different stages of the self-training process listed in this table, and then trying to apply different design choice alternatives for each stage. We try to create an enhanced self-training approach by greedily selecting the best design choice for each stage by comparing them on multiple benchmark datasets listed below and choosing the best design choice by a majority voting algorithm. We start with fully supervised baselines, which act as the initial teacher model for self-training. These models are only trained on the labeled subset, as described in this following table. We used a wide variety of architectures in the REST family for each of our datasets. We also applied strong data augmentation policies, following previous work, which found that incorporating strong data augmentation policies acts as a regularization effect to tackle confirmation bias in self-training. We rigorously evaluated 3 different random seed initialized runs for each design choice comparison to significantly test the difference between our design choice options. We report the mean score across the 3 different runs along with the standard deviation in the following table and all the tables for subsequent experiments. The first stage of self-training that we analyze is the loss function choices. We compare between using a hard categorical cross-entropy loss that uses one hard target as ground truth with a soft loss that uses a full cross-entropy loss using the complete softmax prediction as the pseudo-label targets. We found that the soft loss function works significantly better across all 3 datasets, showing that the soft targets act as a regularizer, preventing the model from confidently predicting incorrect one-hot pseudo-labels. Since we apply a greedy strategy, going forward we would be using a soft loss function for all subsequent experiments. We next study the initialization choices for the student model by comparing the fresh training process of training every single student model from scratch with the fine-tuning approach of carrying over the weights from the student model from the previous iterations, having the best validation accuracy. We found that fine-tuning works significantly better across all 3 datasets, showing that knowledge sharing across self-training iterations can lead to better performance. We then add this to the list of the best selected components that we use in our enhanced self-training approach. We next evaluated how we construct a mini batch of training examples during self-training. We compared the random approach of uniformly collecting mini batch examples, which is the most commonly used technique, with our custom split batch approach, which allows the user to specify a given split of labeled and pseudo-labeled examples for every mini batch from a dataset based on the data sizes of the labeled and unlabeled subsets. We found that the split batch strategy works better than the random strategy, as the constant bootstrapping of labeled examples in every mini-batch during training provides additional vectorization that can reduce confirmation bias. We further study different choices of sampling pseudo-labeled examples during training. We compare the naive method employed by non-student approach, which uses handcrafted softmax thresholds and per-class sampling counts to always sample from a balanced subset of pseudo-labeled examples, We compared this with our weighted split batch sampler, which can dynamically reweight and sample examples for each dataset using the per-class lens and normalized softmax confidences that allows us to adapt to each dataset differently. We found that our weighted split batch approach works better on the CIFAR datasets but performs poorly on the SVHM dataset, which is comparatively more simple than the CIFAR dataset, resulting in the naive approach performing better. Hence, by majority voting, we still choose to apply the weighted split batch sampler for future experiments. We further test our proposed calibrated entropy thresholding module that applies temperature scaling to calibrate the teacher model before generating pseudolabels. We then use the entropy of the calibrated pseudolabel predictions to threshold the pseudolabel examples and compare this with the naive method of using handcrafted softmax thresholds to filter out noisy pseudolabels. We found that our calibrated entropy threshold was a better metric to assess the contents of these models, performing significantly better on all three datasets. Hence, we added our calibrated entropy thresholding approach to the list of the best selected components. We finally assessed the ideal teacher size to be used in self-training. The original noisy student approach found that using a smaller sized initial teacher works better for the problem of confirmation bias. However, when we apply all the best selected components so far to our self-training pipeline, we found that even using the same size teacher and student model performs better than the noisy student approach, even when using the smaller teacher model from the noisy student as the student for the same sized approach. Further improving the size of the model improves the performance significantly, showing that the need for using a smaller sized model is not necessary when we apply all our best selected components. We incorporate all the best selected components from the previous experimental comparisons, as described in the slide, to build our final enhanced self-training approach. We next evaluate the generalizability of our enhanced self-training approach on larger datasets with different labeled and unlabeled subset sizes. We test the model in two different scenarios of using a smaller labeled subset of 1,000 labeled examples and a larger labeled scenario of 20,000 labeled examples from the Snington dataset. In each experiment, we sequentially increased the number of unlabeled examples and found that our enhancements work across different settings of labeled and unlabeled subset sizes, showing the generalizability of our approach to bigger datasets and different size subset sizes. We further test the generalizability of our enhanced self-training approach to larger model architectures and more complex datasets like tiny ImageNet, which have more target classes. We increase the model sizes across the datasets and compared our enhanced self-training approach with the original noisy student approach and found that our enhanced self-training approach beat the noisy student approach across all datasets, showing the generalization ability across datasets and different model architectures. In a real-world training scenario, the unlabeled dataset might contain unseen examples in the training data, which was never seen in the labeled subset. We tested our enhanced self-training approach and the noisy student approach on such a custom-built open-set version of CIFAR, where we used the 10 classes from CIFAR 10 as the known classes and the 100 classes from CIFAR 100 as the unseen classes. We test both the approaches out of the box and also by applying an open-set recognition technique using contrastive learning to separate the feature spaces of the known example from the unseen examples. We found that our enhanced self-training approach works better than the noisy student approach with and without using the open-set recognition technique, showing that our pre-built enhancements work as an open-set recognition technique as well, on top of reducing confirmation bias. To summarize, in this paper, we evaluated multiple design choices to tackle the confirmation bias problem in self-training. We built an enhanced self-training approach by using these design choices and showed that our approach works better than the original noisy student approach across different datasets in different training settings. In the future, we plan on incorporating the open-set recognition inside the self-training process without having to apply a separate contrastive learning process to operate in an online fashion. We further plan on testing the enhanced self-training approach to real-world datasets such as satellite imagery datasets or synthetic aperture radar-based datasets. Please refer to the paper for more details and experimental analysis. Thank you.